So welcome everybody to this new session of QRST seminar. And today we have Christine Muschik and Jesse Ryan Stryker from Maryland and Waterloo. And they will present, Christine will present this measurement-based variational quantum eigensolver. And just to remind you, everyone what is the format of these talks, we will have 2 talks of 25 minutes each, plus 5 minutes for questions. And in case that we are running out of time, you can just type your questions in the chat and the speakers will answer them after the talk, or just stay a little bit longer after this hour of seminar and we will continue the discussions during a few minutes extra. Everything is recorded and will be uploaded in our YouTube channel together with the slides of the speakers and the chat history of Zoom. I believe that's everything. So let me introduce you, Christine Muschik from Waterloo. Christine joined the Institute of Quantum Computing in 2017 as assistant professor in the Department of Physics and Astronomy. In Munich, Muschik, sorry for my bad pronunciation, studied physics at the Ludwig-Maximillians-Universität. She completed her dissertation at the Max Planck Institute of Quantum Optics under the supervision of Ignacio Cirac. And her theoretical research in quantum optics earned her the Alexander von Humboldt postdoctoral fellowship at ICFO in Barcelona as part of the Maciej Lewenstein quantum optics group. Muschik continued her postdoctoral research in IQOQI in Innsbruck, Austria with Peter Zoller. And she joined the University of Waterloo from the Institute of Theoretical Physics in Innsbruck, where she was a university assistant. So welcome, Christine, and looking forward for your talk.
Thank you. Thanks, Alba. I'm very happy to be part of this Toronto seminar series. And this talk, basically in a nutshell, to give you the executive summary just up front, is basically about hybrid quantum classical algorithms. So about VQEs, variational quantum eigensolvers. So these schemes, the existing schemes, are based on quantum circuits. And here I'm going to talk about a different approach, which is not based on circuits, but which is measurement-based. So hence we call it measurement-based VQE, MB-VQE. And yeah, just in a nutshell, your good old circuit-based VQE, it has entangling gates, local gates, and measurements. And if you go over to this new type of scheme, measurement-based VQE, you start from an efficient resource state, and I call it efficient because yes, it's entangled, but it's also efficient to determine and to produce. And once you have this resource state, you just perform local gates and local measurements on it. And however you prepare your efficient resource state, it's entirely up to you. You can use gates or you cannot use gates. In principle, you can do everything just locally, local gates and local measurements. And this is a very complementary approach. I do not recommend it for like every type of problems, but there are some problems for which it is advantageous. And this is mainly because it's so different that it just ends up having very different resource requirements. So hence enlarging the toolbox for VQEs. And taking a step back, the bigger picture, the vision is really looking at this concept of a universal one-way quantum computer, a universal measurement-based computer, and like transforming it into one-way quantum simulator. And I'm really thinking here about the one-way quantum simulator, which is special purpose for the purpose of this talk. So there will be a different type of simulator for chemistry problem or for high energy physics problem, which is very NISQ friendly to take the stance of a special purpose quantum simulator, one-way quantum simulator in our case. You will find all the details in this archive publication. Our first author is Ryan, who really did amazing work. This is his master's thesis, and he worked together with the postdoc Luca Dell'Antonio. So Luca is a postdoc on this project, and together the two of them really pulled this off, and none of this would have been possible without our external collaborator Wolfgang Dürr, who's in Innsbruck, and he's a world-leading expert on measurement-based quantum computation. Of course, all authors contributed, but I want to give upfront my special thanks and special kudos to these three. And with this, let me dive right into our talk. So it has 5 short sections. I start with an introduction, then I will give a short, probably too short, introduction to measurement-based quantum computing. And then I'm going to walk you through our 2 schemes that we propose. And then it will be already time to wrap up with the conclusions. So here comes the introduction. So everything is about variational quantum eigensolvers. And since, Alva, you're putting on the seminar series in Alain's group, and this is of course a stronghold, so I just point to the review article, and I'm not spending much explanation here, just 2 sentences. A variational quantum eigensolver consists of a closed feedback loop between a classical computer and a quantum computer. The classical computer runs a classical optimization algorithm, and the cost function evaluations happen on the quantum computer efficiently. And applications are just wide-ranging. Chemistry, particle physics, something that we are doing in my group, but also classical optimization, sensing, many-body physics, you name it. So it's a very versatile tool. And well, it has this quantum computation aspect in it. And for quantum computation, it's so well known to do quantum computation based on the circuit model, right? But it's of course not the only one. There are several ones. I mean, measurement-based quantum computing is one of them, but there's also adiabatic quantum computing, dissipative quantum computing. All of them being universal. And here on the slide, I'm just comparing circuit-based and measurement-based. They're equivalent in terms of the scaling of resources. However, in practice, if you want to do it, well, it turns out to be different. So if you have a circuit-based quantum computation, typically you're limited by 2 things. You're limited by the size of your qubit register, especially now in the NISQ era. And you are also limited by the number of gates that you can perform. Like I'm talking about the circuit depth here. And this has 2 reasons. The first one, maybe coherence time is an issue, quantum memory time is an issue. However, it's also about the fidelity with which you can do your entangling gates, right? So let's think about trapped ions, for instance, where you have essentially a perfect qubit. But then if you apply a gate, you introduce your errors because it's just a technical control problem. And then it limits how many gates you can do. Well, because errors just accumulate and at some point become overwhelming and dominate the computation. So these are limitations, very typical limitation for circuit-based computing. Measurement-based computing is different, as I will explain more in the next section of this talk. But basically, you start from an entangled input state. You have a lot of entanglement to start with. It's not that you generate it throughout the circuit. You start with it, and then you use it up. Hence the name one way. Because afterwards you have destroyed your resource state. And the computation is performed by performing single qubit measurements, and this realizes your gates, as you will see. And this usually is limited by the state that you can, how powerful the state is that you can start with, and especially how big of a state you can make. So that's for the 2 computation models. And so what I'm going to talk about now is what we call measurement-based VQE. It's a new variational technique, and it's based on the principles of measurement-based quantum computing, so hence the name. And the task that we're tackling here is a very prototypical task for VQEs. Go ahead and prepare the ground state of a target Hamiltonian of interest. Has, of course, wide-ranging applications, chemistry, condensed matter, particle physics, very generic task. And the main idea, as you will see, is to use not a universal input state, but a tailored entangled state as resource, a small custom state. So I call it a custom state. I will call it a custom state throughout this talk because it's for one type of problem. So for a chemistry problem, you need a different custom state than for high energy physics problem. It's similar, like in a VQE, use a different ansatz for one problem than for another. And and these custom states are problem specific and can be small. Yeah? This is what I also alluded to in the beginning. Instead of doing the universal one-way computer, you do something problem-specific with a problem-specific state, a special purpose one-way quantum simulator. So this is what everything is going to be about. And I will introduce two schemes, scheme 1, scheme 2. Scheme 1 is a direct translation. If you already have a VQE, which is based on a circuit, how can you make a measurement-based VQE out of it? And a concrete example is the so-called Schwinger model, you will see. Scheme number 2 is something that we call edge decoration. So you will see what it is. And it's just a new type of state variation. And there's no direct analogy to the circuit-based version. And you will see by me introducing a concrete example, the toric code model. And with this, let me just give you a very quick overview to how measurement-based quantum computing works, and then I can show the two schemes. Okay, measurement-based quantum computing. Yeah, these are two good references, especially the second one. The guys in my team even started calling it the Bible because it was so useful for everything we did. And here I'm just quickly reviewing how you make a universal set of gate in measurement-based quantum computing by first showing how you do a single qubit rotation and then showing how you do a CNOT. And this means you can do absolutely everything. Okay, an arbitrary single qubit rotation. Well, about an arbitrary axis, but also an arbitrary angle. You can always decompose it into an X rotation, a C rotation, and an X rotation. And if you specify 3 angles, you have specified your entire rotation. And how you go about it in measurement-based quantum computing is, well, you start with the resource state. You can make it however you like. If you want to make it with gates, you can prepare 5 qubits in the plus state and apply CZ control C operations whenever you see a link. This is an entangled state, and the different qubits play different roles. The first qubit is the input qubit, then 3 qubits are ancillary qubits, they help you to rotate, and the last qubit will be left in the end because it's your output qubit. So what you have to do, measure the first 4 qubits and choose different measurement bases. Measure the first qubit in X, and the 3 ancillary qubits measure them in a rotated basis. Yeah, so the rotated basis is defined here. If you want the X measurement, just set phi equals 0. Okay, and then you get measurement results 0 or 1 for the first, second, third, and fourth qubit. And so here's the clue. If you measure your second qubit, you have to know which rotation you want. So the angle θ1 factors in, yeah, for your first X rotation, but it also depends on your measurement result. So hence it's an adaptive measurement. And this holds true for also the next 2 rotations. You have to know which rotation you want. So you have to know the Euler angle, but you also need to know the previous measurement results. And then if you do this, the measured qubits, well, they're gone, they have been measured. You're left with your output qubit. And what you have applied is the intended rotation, and you have a byproduct operator, which you didn't want, but well, you get what you get. It's just a Pauli string, you know what it is if you know the measurement outcomes. And so this is an example of about an adaptive measurement pattern. So you measure in a certain order and you adapt the next measurement on what you found earlier. There are also non-adaptive measurement pattern like the CNOT operation. Yeah, CNOT is a Clifford gate, so all Cliffords are non-adaptive. So you're free to perform measurements in any order that you like, or even to make them simultaneously if you prefer. So here's the CNOT. Yeah, it's a state that you have for the CNOT. And as you see, your measurement pattern involves only measurements in X and Y. Well, do it in whichever order you please, do them simultaneously. You will have completed your CNOT. This already brings me to the first important point, which is something that we're going to use in our proposal. It's a concatenation of measurement pattern. So this little mini circuit on top, the orange thing is a rotation about the C direction. Yeah, so here I'm only using the middle one here. I only want to rotate around the C axis. Then I do a Hadamard, a CNOT, and a Hadamard. And how you concatenate it is like you take your big cluster state in this case, and then make sure that the output of one is the input of the next. And as you can see, this is something which has 3 fixed gates. The Hadamard and the C0 are fixed. They're also all 3 Cliffords. And the only one which is non-Clifford is the arbitrary rotation around the C direction. Thinking already about the VQE, this will be my knob, yeah, the variational parameter. I can use the Gottesman-Mill theorem for efficiently calculating that, carrying out efficiently the part of the circuit such that you get a much smaller resource state. So yeah, I think it's obvious how the smaller 3-qubit state is much more compact than the big thing on top. And it's just, yeah, I contracted everything, carried out the fixed Clifford part of the circuit, and I'm left only with 2 output qubits and like 1 knob. And that's already the secret of scheme number 1. Yeah. So scheme number 1, I'm introducing just first the general idea, and then I give you a concrete example. The general idea is you have a VQE, but you would like to have a measurement-based VQE. Yeah? How to turn your normal VQE into a measurement-based VQE? Well, here's an artistic view of the circuit. Here we distinguish between Clifford parts like Hadamards and C0s and non-Clifford gates. And specifically, I'm thinking here of the standard scenario where, yeah, you break your circuit, your VQE circuit, into fixed parts and variational gates. And the variational gates, as if you go to do something on Google or IBM, or you will have the variational gates for the local gates, which are knobs. And then we translate it into a small custom state. And the small custom state, the size of it will only depend on how many knobs you have. And then you perform measurements on it. So that's the general idea. And it's useful if you have a circuit, if you have a large Clifford part, because that's basically for free. It's absorbed in your custom state. And our concrete example is the Schwinger model. Schwinger model is just quantum electrodynamics on a 1D lattice. And yeah, we chose it because it's something that we're working with a lot in our research, but also because it's a benchmarking model for quantum simulations of lattice gauge theories and yeah, particle physics simulations in general. You can go and take your 1D QED and cast it in a spin model. So the details are actually not important here. It's just for you to see it's a spin model. It has Pauli matrices in it. It has 2 body terms, but weird long range interactions. So it's a kind of an exotic spin model. And yeah, you can write the circuit for it. Actually, I could have written a much better circuit, but this is a generic circuit. Yeah, we wanted to have something very general, a generic VQE circuit for the Schwinger model. With this prescription, fix your C0 gates, have all your variational parameter and single qubit gates. Then you have just a lot of layers, and each layer is just simply locals entangling, and entangling in our case is C0s. Yeah, and then you repeat it over and over, locals entangling, locals entangling. And this is good, and it's maybe not optimized, but it's good enough to simulate the Schwinger model, and we can translate it into a measurement-based fashion in the way that I introduced earlier. So each layer, you have the circuit for a layer, and you translate it into a custom state, carrying out all the Clifford part already, leaving only the knobs. So you see we have 8 knobs in the circuit, so our custom state here has also these knobs, and then yeah, you have a measurement pattern that walks you through. And I don't have much time here. I will just flash some results. The details are again not so important. It's just a phase transition that happens to be observed, that can be observed in this model. Actually, with trapped ions, with our experimental collaborators, we saw it with up to 20 qubits, yeah, with a bit more optimized circuit. It's just an order parameter that brings about this phase transition, and you need up to 4 layers. These results are like completely equivalent, whether you do it circuit-based or measurement-based, in a measurement-based way. K is the number of layers. If you're close to the phase transition, you need more layers, of course. But what this illustrates is 2 points. A, it works, of course. And secondly, it sheds a light on how the resource requirements are really different. Yeah. So for the VQE, you have your bunch of entangling gates. The more layers, the more entangling gates. And if you have your measurement VQE, well, there are no entangling gates, but you have your resource state. And the resource state really just depends only on the number of knobs, not on the Clifford part. So if you are in a situation where where it's either difficult to make entangling gates or where you cannot have long gate sequences, then this kind of would be an alternative. Since I don't have so much time, I don't talk about the required coherence time, but I will be very happy to answer questions on the coherence time afterwards. For now, since I have only 6 minutes left, let me jump right into scheme number 2, which I'm personally very excited about. And we call it state variation by edge modification. Again, I'll show you the general idea, then I show you a concrete example. The general idea has been beautifully depicted by Luca, who came up with this airplane metaphor. So let me explain you what it means. So the general idea is, well, you have Hilbert space, but you start in a suitable corner of Hilbert space. And how do you get to your suitable corner of Hilbert space? So how do you get to your island? Yeah, well, it's your ansatz state. Don't worry, I will explain the ansatz state, which looks slightly complicated in a minute. But your ansatz state brings you all the way to the appropriate corner. And then your variational algorithm, your classical optimizer, then only optimizes locally here. So it's a runner who's only walking on foot. Yeah. And here's an example. Yeah, suppose you have a Hamiltonian, which consists of 2 parts, a Hamiltonian and a perturbation. And then you can, for instance, use as an ansatz state the ground state of the unperturbed Hamiltonian. And the ground state of the total Hamiltonian can be totally unknown, but you expect it to be close to there. And then you let your VQE explore this region. I mean, you don't have to be in the scenario that it's a perturbation and a known Hamiltonian. It can be whenever you have an educated guess that can be cast in the graph state language. So translating this to Luca's metaphor is you want to go on vacations, you go onto a plane which brings you all the way, that's all the entanglements, it's already in the ansatz state, has already the right entanglement structure. And then the VQE is basically exploring your island. And if you want to solve a different problem, it would mean choosing a different holiday destination. You go to a different airport, but it means you need a different ansatz state. So hence it's problem specific. Okay, this is maybe a busy slide, so let me walk you through more slowly. And it's best seen with a concrete example. So our concrete example is a perturbatory code. And to the best of our knowledge, well, it's not known how to calculate the ground state efficiently. So our H0 is a toric code Hamiltonian. Well, and for this, we do know the ground state. And it's also a graph state and can be determined efficiently. But as soon as the perturbation is added, all hell breaks loose. Yeah? And you don't know what the ground state is anymore. Our perturbation are local sigma c terms. So think about fluctuating magnetic fields that are causing this perturbation. And so what we do here is you take your ground state as the ansatz state. So this nice little picture down there is the graph state representation of the ground state of a ground state of the toric code Hamiltonian. And now we decorate it, and I will explain this now in a minute. So you take the ansatz state and you decorate it with all the orange stuff, and then you get the custom state. Okay, and this edge decoration is you take your custom state, which is the ansatz state plus auxiliary qubits. So in the toric code example, you can of course modify this. Whenever you have an original edge, you decorate it with auxiliary qubits. So if you look here, look for instance at the edge in the very left corner and replace this edge with the decorated edge, then you get this bigger custom state. And the fate of these orange auxiliary qubits is actually to be measured. They're not going to stay long. And the thing is, if you measure these orange qubits, it will have an impact on the white qubits will stay behind. It will modify the entanglement structure and it will modify the state. So measuring these orange auxiliary qubit results in a state modification. So how does this work? The state variation protocol means that the auxiliary qubits are measured to modify the custom state. So it's a classical algorithm, the classical routine, which selects the rotated measurement. So it selects the angles in which you measure. And depending on which angle you measure, well, the state is modified in a different way. And you modify it in such a way that the cost function is minimized. There are some results, but it's just to show that it works. And yeah, this hopefully explains the edge modification perspective. So with the last minute, I will just conclude. I showed two schemes, and we strongly believe they can be experimentally explored already today. So the full toric code example would be 44 qubits, but you can easily construct a minimal instance with much fewer qubits. So instead of the toric code, you can go to the planar code. Instead of insisting on having something deterministic, you can switch to something probabilistic for first proof of concept demonstrations. And we envision good path forwards for platforms such as superconducting qubits, where measurements are fast, but especially for photonic platforms, which are a bit hindered by the fact that entangling gate operations are so hard. And especially these two publications in 2020 that you see here provide all the capability, like really exciting perspectives for making these custom states. And of course, for future directions, we want a detailed analysis of noise robustness. But for this to be meaningful, it should be for specific platforms. I'm looking forward to working this out for specific implementations. And last but not least, it will be extremely interesting, and I really like to do that, to explore new tailored edge modification schemes. Because this edge modification that I showed you, it really doesn't have an efficient representation necessarily in the circuit approach. It's like a new way to think about state variation and conceptually different VQE design possibilities. And this is the big picture agenda, and I want to finish with just thanking the team, especially these three people, and of course, thank you for your attention.
Thank you, Christine. Very interesting talk, especially for at least me, that I was not familiar with measurement-based quantum computation, so it was very helpful. Okay, any questions? Because I have some. Maybe I can start with, I would like to know more about the coherence time, because it seems that you have many things to say about it.
The coherence time, right? So something that I personally find interesting about the coherence time is there are two parts to the problem, right? The first one is once you have, like the first one is making the custom state, and then the second one is computing on the custom state. And if I make the custom state, actually the required coherence time is constant. So it does not depend on like the number of qubits, or it does not depend on like how many Clifford gates I had originally. So if I would make it, if I choose to make the custom state with a circuit, it would have circuit depth 1. So there's just a constant time for the coherence time required to make the custom state. Or like if I'm prepared in a measurement-based fashion, I can just complete all measurements at once if I want. So there's no adaptive thing going on. So that's effective in terms of coherence time. And then of course the computation itself, it depends how many adaptive measurements you have. Of course, if I have a VQE which has almost no CNOTs and has almost no Clifford part, and I'm doing adaptive measurements like all the time, then I will need a lot of coherence time. But if I'm finding a problem which has like a ton of CNOTs, well, there is no reason to bother my VQE with that, to go through all of them. It's instead, I calculate this efficiently through the Gottesman-Mill theorem, put it into my custom state. And so this doesn't factor into my coherence time. Yeah.
Okay,
thank you.
We have another question from Arthur. Arthur raised his hand. Please go.
Hi, Christine. So a really nice talk. Thank you. And I guess I was wondering about the number of entanglement gates that you need to create this cluster state and adaptive measurements. That's another aspect, because in a normal VQE you don't need the adaptive measurement, right?
Mm.
So that is clearly like an extra overhead.
Yes.
And then there is this cluster state, which is auxiliary qubits plus the entanglement of all that stuff. So could you comment maybe, maybe I'm not understanding the setup properly, but it seems like there's a lot of overhead in this new scheme compared to the VQE. Would it be beneficial to use it for, say, quantum chemistry? That's where I'm coming from. And yeah.
Okay, so let me try to answer one step after the other, but let me also say upfront, for quantum chemistry, I honestly don't know, because I have not worked on quantum chemistry problems so far. So we look, like in my group, we're mostly looking at problems that are from lattice gauge theories and from particle physics. So for chemistry, I cannot promise anything, but like more general, we're also in the very beginning of exploring the scheme per se. So now about adaptive measurements. Okay, so adaptive measurements, that there's an order to things, is not so conceptually different, right? So because if you have a normal VQE, you have a circuit, and the order, of course, matters a lot, right? So if you do a gate sequence, then you're obliged to these gates typically don't commute, so you're completely obliged to follow the order. And so this is very similar to our case, where we have to where we have an order. What is new actually in a normal circuit, in a normal VQE circuit, you don't have this kind of if statement. I mean, you don't have this that the next gate is doing something conditioned on a measurement per se, at least not within one layer. Yeah. I mean, in a normal VQE, you still have it that you cannot do the next round if you don't know the measurement result of the previous one. And now we also have it like on a layer, on a loop level, but we also have it in each layer. Basically, so that's new.
I'm generally familiar that adaptive measurements are already been done, and even on the industrial or kind of public accessible level, there is a Honeywell computer that can do it. And in quantum chemistry, actually, we have a publication on the measurement scheme in VQE based on the adaptive measurement scheme. It's just like a theoretical proposal in a sense. It can improve the number of measurements you need to do in a normal VQE. But I guess it's still a little bit like an overhead compared to the normal situation, where you don't need to worry about the previous measurements. You just go and do all of them. In a sense.
Yes, the applications that you mentioned, so I'm not sure I caught that. Can you say it again?
So, yeah, I can send a kind of link. There is a paper that we published, but the idea is very simple, is that in the normal VQE, the question is how many measurements do you need for complicated, say, operator Hamiltonian to measure it, right? And it turns out that adaptive measurement can treat different Hamiltonians all in one run, in a sense. And that is also connected with the fact that those pieces that adaptive measurements can do, they are operators that have a product states as eigenstates. But those product states, they are tricky, because some of the qubits are essentially, their quantization axis depend on the previous qubit measurement. So that extends your range of measurable operators, essentially, if you do adaptive scheme.
Yeah, right. And like I also saw, like in connection to the Honeywell capability, how you can simulate larger systems with smaller ones, right?
Right. Mm-hmm.
Okay.
But I'm a little bit worried with this cluster state, like that you need auxiliary qubits, and that you need to entangle all of these qubits. And like looking at your plots, it seems like there are lots of qubits you want to entangle. Don't you worry that in reality it's like going to be very difficult in order to get at the end of the day, say 5-qubit entangled state, you need to entangle like more than 20, and then
I don't need to do that. This was maybe misleading. I apologize. I mean, one way, but it would be a stupid way, which I don't recommend, like how to get the custom state, right? Because the VQE cannot be started if I don't have the custom state to start with. Okay, so how do I get the custom state? I do not recommend to make a huge cluster state and then measure in order to get the custom state. So that, I mean, you can do it maybe on paper, but I do not recommend to make this in practice. Yeah, so in practice, one should directly prepare only the small state, because if you go through the cluster state, that's exactly what we wanted to avoid. Yeah, because the cluster state is like gigantic, like way too many qubits. Yeah, the whole point is I have a special problem. I don't need a universal cluster state, even less like such a big one. Yeah, I need like a special small state, and then I only used to explain how you get to the idea, but like you should absolutely make the small state directly. You should not go through this big cluster state.
Okay.
Sorry for interrupting, but we should move to the next talk.
Yes.
Thank you very much.
We can stay long. I encourage you to stay a little bit longer once you finish, so we can continue with these discussions. And there are actually more questions in the chat, so please, Christine, feel free to answer them and continue the discussion with Arthur, of course.
Thank you.
Okay, sorry for that.